Thank you, Sergey and Anton for having me, and thanks everybody for being here in numbers. So this talk is about natural language processing, and in particular word embeddings, which are a family of algorithms that are kind of gaining some traction right now. A couple of words about me. So I'm based in London. I co-organize the PyData London meetup and conference. So we run a monthly meetup, kind of similar setting, couple of talks, nice people, few beers and so on. And we also run our annual conference. It was back in May, also in London. And on the right side, you see some work that I've done. This was a book published last year on data mining for social media. So the job title is data scientist, whatever that means. And in particular, I try to focus on text analytics. So word embeddings, the structure of the talk will be kind of an informal introduction on word embeddings first, what they are, what we want from them. And then a little bit of theory, but not too much. This is meant to be really an introduction, so if there are machine learning experts in the room, maybe you will not learn too much on the machine learning side, but it's more on the linguistic intuition. And then a bit of Python at the end. So terminology, word embeddings are vectors that represent words. So what you see here, they're all synonyms. Word embeddings, word vectors, also semantic vectors, because these vectors capture the semantics of words. And also distributed representations is another way to call word embeddings, because the meaning of a word is distributed across many dimensions. So why is this important? Well, in data mining, the way you represent your data is crucial for the success of your application. And in text mining, that's the same story. So word embeddings are really interesting ways of representing text. In terms of applications, where are these word embeddings useful? Really anything about text analytics is fair ground to try out some word embeddings. I'm just mentioning a few bullet points here, but that's not an exhaustive list. So classification or tagging, assigning classes to documents, recommendation systems, search engines, so you type in your query, and then the search engine can expand your query and understand what you're trying to search. And then a bit more difficult, machine translation, so going from English to any other language. These are all applications where word embeddings have been applied successfully, and there are many more. So really everything about text analytics is a fair game. I want to start with a couple of ways of representing text. So the first one is the classic one-hot encoding. So in one-hot encoding, you have also vectors representing words. And you see you have zeros everywhere, and then you have only one bit being hot at a time. This is good to represent categorical data. And you can use it to represent words as well. So essentially, every dimension that you have there is representing a word. So first bit for Rome, second bit for Paris, and so on until the last word. There's a problem here. We are basically having a lot of dimensions. So the size of your vocabulary potentially is huge. So there's a dimensionality problem. And also, we don't have any notion of similarity between these vectors, because these vectors don't have any dimension in common, right? So you cannot calculate easily any kind of similarity. Another approach to represent text is the popular bag of words. This is used usually to represent documents. So with documents, you also have vectors, for example, and again, each dimension is essentially representing a single word. This could be, how many times you see the word Paris in document 1, that's 14. How many times you see the word Rome, that's 32. That's a row count. You could normalize it in many other ways. But again, you have a big number of dimensions, and at least you start having some notion of similarity, because you might have some dimensions in common here, so you can compute similarity between vectors. Now, moving on with word embeddings. So word embeddings are also vectors. The example is kind of made up just to showcase a couple of aspects of word embeddings. So what we want from word embeddings, we want the number of dimensions to be much smaller than the vocabulary size. And then we want to capture some ideas of similarity. So for example, Rome and Paris are somehow similar. Okay, they're both cities, they're both in Europe, they're both capitals, they are both nice places to visit. So a few dimensions, you see the numbers are kind of close to each other. Similarly, Italy and France, they're both countries, they're both in Europe, good wine, good food, and so on. So you want to capture this similarity with some dimensions. Also, Rome and Italy, and Paris with France, they are kind of similar to each other in the sense that there is a semantic relationship. So Rome is the capital of Italy, and Paris is the capital of France. And this semantic relationship, you want it to be captured as well by some of the dimensions. Once you go into kind of pictures, if you try to picture it, you see Rome and Paris as vectors. They're close to each other because they're similar. Italy and France as well, they're close to each other because they're similar. And you see there is almost this direction from Rome to Italy and from Paris to France, which is representing the relationship of being capital of. And that's the nice aspect with word embeddings. So you can do vector arithmetics. You start with a vector for Paris, you add the vector for Italy, and you remove the vector for France. You will end up with a vector which is very, very close to the vector for Rome. Okay, so you can perform this analogy task. And maybe you've seen before the king minus man plus woman equal queen. That's also an analogy. So we don't have vectors yet, we have language. So what is the main linguistic intuition behind these models? That's called the distributional hypothesis, and this is nothing new. Okay, this goes back to the 50s. And in particular, you find a reference, usually every talk about word embedding is referencing this particular quote. You shall know a word by the company it keeps, by this British professor of linguistics, 1957. And maybe it sounds a little bit too intellectual, so there is another one from a couple of years earlier, which is probably more clear, straightforward. Words that occur in similar contexts tend to have similar meaning. Okay, so that's as simple as it is. We can use the context, so what's going on around a particular word, to approximate the meaning of the word itself. And I want to give you an example. So this is a sentence. I enjoyed eating some pizza at the restaurant. We focus on what's important, so that's the focus word, the word pizza. And everything else is the company keeps. So that's the context of our word. And essentially, we can approximate the meaning of the word pizza just looking at the context. Okay, so pizza is something that we eat. Pizza is something that we have at the restaurant. Pizza is something that we enjoy. And then you scale it up on thousands of sentences. You see how the word pizza is used in the sentences. And once you aggregate, you end up with the true deep meaning of the word pizza. And now I give you a counterexample. So you have two different sentences. I enjoyed eating some pizza at the restaurant, and I enjoyed eating some Weisswurst. Did I spell it right? Yeah? Okay, so these are two different focus words. And maybe you already see where this is going. So we have the same context. According to what I told you so far, same context, same meaning, okay? So for some people, maybe having pizza or Weisswurst is the same thing. For me, this is kind of outrageous. Don't blame me, blame the data. That's what the data look like. That's what the model is going to pick up. Okay, so this is just to have a bit of fun with a simple example, but really it opens for a discussion on data quality. Your model is only going to be as good as your data, and possibly about ethics, because language is going to be biased. It will pick up the biases from your culture, and your model is going to pick up the biases from your language. Okay, now moving on with a bit of theory, I'm going to mention in particular the word-to-vec family of algorithms. So word embeddings are a family, and word-to-vec is kind of a family within the family. And word-to-vec is what started all the interest a few years ago, around 2013, on this word embeddings and on doing arithmetics with words. So this is work that has been done at Google. So Thomas Mikolov and colleagues published a couple of papers in 2013. Efficient estimation of word representations in vector space, and also distributed representation of word phrases and their compositionality. And the concepts from these papers, they ended up in what we know today as word-to-vec. So about the vector calculation, so how do we get vector from language? The goal then is learn vectors that represent words, and we're going to look at things from a distance, from the high level. So first step, choose an objective function. Second step, initialize randomly our vectors. And third step, run stochastic gradient descent until you end up with the vectors. And if you've done some machine learning before, maybe you've seen the same approach applied to many other different contexts. Okay, so from a distance, sometimes machine learning looks kind of everything the same. So what's interesting here is really what's going on with the objective function. Okay, so the objective function is something that we want to maximize, and we call it gain function, or something that we want to minimize, and in that case we would call it a loss function. And I go back to the example. So we have the sentence, the focus word is pizza, and that's our context. So the objective function in this case is we want to maximize the likelihood of observing the context given the focus word. In other words, we're going to end up with a bunch of probabilities that look like this. So probability of observing a context word given the focus word. Okay, let me look at the example with a few more details. So we have our sentence as before. We have our focus word, and we need to iterate over all the context words. So we start from the beginning of the sentence. We see the word I, given that the focus word is pizza, so we bump up the probability of I given pizza. And then we move on. We see the word enjoyed, given pizza, and we bump up the probability of enjoy given pizza. We see the word eating, and we bump up the probability, and then again and again until the end of the sentence. Once we reach the end of the sentence, we move on to the next focus word, and we repeat the process. So starting from the beginning, you see I given the word at, bump up the probability. You see enjoyed, bump up the probability, and then you see where this is going. So essentially, two nested for loops, and then the core, the heart of the matter, is bumping up these conditional probabilities. And I keep saying bump up the probabilities, but we haven't defined any probability yet. So what's the probability of eating pizza? Question mark. We can generalize. We call the condition, the word pizza in this case, the focus word, also input word, and we call the context word also output word. And we want these probabilities to be dependent on the vectors. Okay, so we kind of rephrase the probability as a probability between vectors. So using this notion of input and output, we can rephrase it as observing or bumping up the probability of the output vector given the input vector. And again, we've been rephrasing, but we haven't defined any probability yet. Okay, so we have this probability defined as vectors. Ideally, we want the probability to be high if the vectors are similar. So first idea that comes to mind, use cosine similarity or other notions of vector similarity. That's a fair intuition. There's a problem here. Cosine similarity is not a probability, right? It's a number between -1 and 1. Next idea, take the cosine similarity and throw it into a softmax function. The softmax is used in many machine learning approaches. It gives you as output a number between 0 and 1. So it looks like a probability, and it turns out it also has a probabilistic interpretation. If you want a formula, that's the formula. So the probability between vectors is essentially defined as the exponential of the cosine normalized over the sum across all the vocabulary, so all the exponentials for all the cosine similarities between output word and input word. Okay, if you have done some machine learning before, this is kind of maybe nothing new. If you're new to it, don't worry too much about the formula. Try to look at things from a distance. So just to recap this idea of computing vectors, what we've been doing, we've been learning word vectors using stochastic gradient descent on the softmax probability as defined before. So here you have all the ingredients that you need to apply this algorithm if you want to look it up. If the theory was not enough, there is more. It turned out you can also learn not only vectors for representing sentences, but also for representing, sorry, not only for representing words, but also for representing sentences or documents. And this is a follow-up work also from Google. And in that paper, they call this algorithm paragraph vector. And just as a reference to word2vec, they also call it doc2vec. And what we have here is pretty much the same. The only difference is how we define the probability between vectors. We also attach a label as a condition, and the label could be a sentence ID, a document ID, anything kind of ID that you use to group all your words into a particular paragraph. Okay, and that's really enough for the theory. Of course, I haven't given you too many details, but that's kind of the overall idea. Now moving on with the practice. So word2vec became popular because it was an academic success on one side, and also because Google released the software as open source. So there's a C library for training your vectors. Excuse me. And they also released the binary form for some vectors that were pre-trained on some Google News corpus, so billions of words that you can use. So essentially, you kill the training times to 0 if you reuse those vectors. We're doing Python anyway, so let's look into Python. For Python, we have this library, GenSim. The punline for them is topic modeling for humans. So what they do is they implement a bunch of NLP text analytics algorithms, and they stick a nice interface, easy to use interface on top of it. And when they implemented the word2vec algorithms, it turned out the GenSim implementation in Python was faster than the original C implementation in Google. So that's how they got a lot of traction. So Python faster than C. There's a lot of Cython and crazy NumPy kind of optimization. So that's how it was possible. Anyway, as users of the library, we only look at the interface, which is Python, so very, very simple, easy to use. Okay, so pip install GenSim, or if you prefer, conda install GenSim. If you do data science, you should go with conda, and you're good to go. And I want to give you a couple of examples of how to use this vector. So this is some work that I did with a previous client of mine. They have kind of a recruitment platform, so you upload your CV, companies upload job specifications, and then the machine learning magic in the middle tries to match the best people for the job. So essentially, we were looking at CVs and the skills described in a CV. So we did a little bit of a pilot to see if word embeddings could be useful. We had a data set of 300,000 CVs. Each CV has a bunch of experiences, and we treat each experience as a sentence, and each experience has a bunch of skills associated to it. Approximately, we had a vocabulary of 15,000 unique skills, so unique words, so not a huge data set. And that's the GenSim part that you need. So essentially, you import the class. You have your data set somewhere in JSON, CSV, any kind of format, it doesn't really matter. The custom part that you need to implement is your corpus reader. So the third line, the class will be probably a generator that yields one experience at a time. Okay. You don't need to load the whole data set in memory, only one item, one sentence, one experience in our case at a time. And then you pass the generator to the Word2Vec class to load the model. And there are a few extra arguments there that I'm kind of hiding the details to keep it simple. You can choose a couple of options. You can choose the number of dimensions for the vectors and so on. So you end up with a bunch of vectors, and you can look at vector similarity. So for example, we have the word chef, and we look at similar words. And the first one is the most similar one to chef, cook, so they are synonyms. That's perfectly fine. And then if you carry on, you see bartender, waitress, restaurant, and other related words. These are not really synonyms, but they are similar in the sense that they kind of belong together. Okay, it's the restaurant business or the food industry, if you prefer. So it makes sense. The word chef also has another meaning. If you are an infrastructure engineer or DevOps, chef might be one of the tools that you use. It's the name of a library. So this is the magic with word vectors. You can do arithmetic. So take the vector for chef, remove the vector for food, and you end up with a vector which is very, very similar to Puppet, Ansible, Salt. These are all libraries in the DevOps kind of space. So essentially, the model was able to pick up these nuances of the language. So the main meaning of the word chef is, let's say, the obvious one with the restaurant business. And then also doing this arithmetic, we were able to see, to observe this kind of similarities. So the model was very, very useful for the data exploration phase, really understanding our data. It was crucial. And also we put it in production later for query expansion and query suggestion. So again, you type in your job spec as a company and you see what kind of skills belong together. And finally, for recommendations, so the algorithm for recommending people and jobs was influenced by the embeddings. Now, on a lighter note, different kind of use case, a bit of a side project for me. I like data, I like Python, I like beer. So why not putting everything together? So there's a data set for research of beer reviews, around 3 million documents, and all the beers are classified according to the beer style. So there are 89 different beer styles, and you see the numbers, a bunch of and many, many words in total for this data set. I'm using Doc2Vec in this example, but the snippet looks very similar. So you import the class first, you have your data, this time it's CSV, doesn't really matter. The third line again, it will be your custom corpus reader. And because we are using Doc2Vec in this case, the corpus reader is a generator that is going to yield one review together with the beer style as a label. If you remember the probability for Doc2Vec, it has an additional label. And I used the beer style as a label. Load it as the model, about 1 gigabyte of data, so 3 million documents, 1 gigabyte of data, approximately 3.5 hours on my laptop. There's a bit of pre-processing, so the model maybe takes 2.5, 3 hours. So suggestion is remember to pickle. Okay. If you close your Jupyter notebook before pickling, you need to waste another 3.5 hours. So now you know that it took me 7 hours the first time. Okay, so we have document vectors here, so docvecs, as you see, and we're looking for similarity between these labels, these beer styles. So stout is the name of a beer style. It's a type of dark beer, and if you look at the most similar document IDs, if you want, you see different variations of stout, so dry stout, sweet stout, and so on. You see porter, which is also a dark kind of English style of dark beer. And if you carry on with the list, you will see all the sort of dunkel and still dark beers that are less similar to a stout, but still they belong to the to the dark sort of a category. So it all makes sense. Once you load the doc2vec model, you also have vectors for words, so you still have the word2vec as well. So you can check what are the most similar words used to represent the word stout. So stout is dark beer. The aroma should be kind of like coffee or chocolate if you want, so you will find coffee and espresso as terms used to describe this kind of beer. You see charcoal as well, because sometimes it's a little bit too much on the charcoal side, so that's also words that are used to describe the beer. Bean is probably coffee bean as a phrase. It all makes sense, okay, if you know about beer and about stout in particular. And as a counterexample, let's say we look at wheat beer, wheat ale. The aroma is kind of like lemony, orangey, zesty, so coriander seeds. Again, it all makes sense. Wheat beer, so the data set is a bit biased in favor of American styles, so these are probably American wheat beer rather than Hefeweizen if you want. So don't get too upset about this, that's just the data. Now, we have this 89 different styles of beer, so I took the vectors. The vectors have a number of dimensions, 300 if I remember well. Throw them into principal component analysis, PCA, to squeeze them into two vectors, so we could visualize the vectors on a screen. We don't have a clear clustering here, but it still makes sense. So on one side, we have all the dark beers, imperial stout, variations of stout, dunkel and whatnot. We have all the strong high alcohol beers together. Then we have the sour beers on a different league. Bottom left, we have all the lagers and pils, kind of German and Eastern European styles, wheat beer as well, and so on. So even though you lose a lot of information when you go from 300 dimensions into 2 dimensions, it still makes kind of sense. And maybe completely random, but I notice on the X dimension, we have the color, okay? So light beers are on the left and dark beers are on the right, and kind of brown, orangey, copper kind of colors are in the middle. Maybe it's random, maybe not, it's not. So the obvious. How many dimensions did you reduce to those two? At the beginning, 300. So each word vector has 300 dimensions. That, as a rule of thumb, not less than 100 and not more than 1,000. It's kind of a good starting point. And so those are binary vectors for each word to reach the top 300 words? After PCA, you have 2 dimensions, yes. And the choice of 2 is just to plot it. You can do 3 and do a crazy bokeh. You know everything about it. 89 styles. 89 documents. So how many documents? 3 million. 3 million? Yes. And so how does what's the complexity? Like, does it scale with n squared, or like if you make more, what's... More on this later. It was a question about complexity and how it scales. So the obvious applications of this is kind of choosing my next beer, which is the point of this evening for me, right? Yeah. And just as a remark, it's really about understanding your data set. Okay, so this is about understanding the language, understanding the bias of the language, and so on. So it's really useful tool as an exploratory analysis, and also I apply it in classification. So comparing to a traditional bag of word approach, it was classifying better. So given a review, can you predict what's the beer style of this particular beer review? Using word embeddings gives you slightly better performances than traditional bag of words, as kind of expected. Okay, wrapping up, maybe you've seen this before, in particular approaches in general based on co-occurrences of words that they've been around for a while, distributional hypothesis from the 50s. and then LDA, LSA, singular value decomposition, and all the friends. It's true. There's nothing new on this idea, but usually these approaches perform better than so word embeddings here perform better than other traditional approaches, and in particular they scale much better because so efficiency. They are based on co-occurrences, but there is no co-occurrence matrix in memory. Okay, you don't load the whole co-occurrence matrix in memory. You only learn the vectors directly. In terms of complexity, so the softmax depends on, it's normalized against the whole vocabulary, so linear complexity against the size of the vocabulary. There's a trick for this, which is called hierarchical softmax, which is also described in one of those papers that I referenced. And I don't remember all the details by heart. Essentially, there's a binary tree as a data structure somewhere, so you go from linear to log proportional to the size of the vocabulary. Classic in machine learning, garbage in, garbage out, so the quality of your input will affect the quality of your output. So the pre-trained vectors that are given by Google for free are useful until they're not useful anymore. In particular, the business domain is important, so they are pre-trained on Google News. So we're talking about specific kind of language, news, and biased towards the US, so US-oriented kind of news. And the pre-processing steps are still important, so what you feed into the algorithm is still important. So the suggestion is, if you have enough data, train your own model. So as a rule of thumb, 100,000 words, probably you can pick up some of the aspects of the language, or maybe not. If you have more than 1 million words, definitely train your own model. That's not a big data set, okay? So that's a generic suggestion for this. And just wrapping up, the first time you see these word embeddings and you do arithmetics, looks like magic. It's really just as a smart application of unsupervised learning. And if you don't care about the theory, I don't blame you. You can just use Python, a few lines of GenSim, and your life is easy. I just want to reference a couple of things, thank a couple of people. So Lev is one of the maintainer of GenSim, is a friend of mine also. He's traveling around the world, so sometimes he's in London, and we've been talking a lot about word embeddings and the work they've been doing on GenSim. And Chris Moody, this guy I never met, I just seen a few of his videos. He has a very nice explanation of word embeddings, and he has also this joint LDA and word embedding model that he calls LDA to VEC. And if you want to know more, the usual suspect, Stanford, and a lot of material online for the word to VEC. Okay, that's essentially closing the talk for me. I believe we have a few minutes for questions. I'll be around anyway, and I'm easy to find online as well. Thank you.
Nice time for questions.
Can you give examples for the 300 dimensions, and how do you define them really? Is that by the algorithm, or is there some human interaction?
How I define the dimensions?
Yes.
So the idea is I don't want a huge number of dimensions, so the vectors it's easier to kind of handle this kind of problem. As a rule of thumb, as I mentioned earlier, less than 100 dimensions, maybe you don't pick up these notions of similarities, and more than 1,000, it doesn't give you more. So people usually start with 200-300 dimensions. That's an empirical kind of observation. That's what you see in many, many papers. And these numbers is purely empirical. So you define how many dimensions you want. It's up to you. By default, if I remember well, you have 300. When you pass the corpus to the word2vec class, you can define how many dimensions you want. As simple as that.
So you take the 300, let's say you define the number of 300, and then you count the words, and you take the
No, you initialize the vectors randomly. So you have 300 random numbers. And then the algorithm looks at the co-occurrences, and it will bump up using stochastic gradient descent. So stochastic gradient descent has the objective of maximizing the probability of the context word given the focus word. So it's run by stochastic gradient descent.
This is pretty cool. Thanks for sharing. Like, this is pretty fun things. So I didn't understand the complexity only depending on vocabulary size. I have a vocabulary of 30,000 words, which is roughly the English language, but it must depend somewhat on how many words you're training, right? I mean, must depend somehow, like if you train on 100 million words in a text, that must somehow go into the complexity of how long it takes to train this thing.
Yes, on the number of sentences, really. So sentence is how you call the context. It could be sentence, it could be paragraph, document. So each sentence essentially will be one of those nested loops.
Oh, I see.
And then the bigger picture is what dominates really the story is anyway the size of the
words.
vocabulary.
So a quick other question on priors. How do you let priors flow into this? Like if you have prior knowledge on, like, I don't know, a beer is related to alcohol, you want to put this knowledge in rather than, like, don't know, let the machine figure it out because you know that already. How do you let this flow into your model training? Yeah,
you don't. You let the algorithm picking up the language depending on how the language is used.
Okay, so you're limited to your training set. You cannot add priors to your model.
Which is when I gave you the example of pizza and Weisswurst. So essentially, your data set will affect the quality of the vectors, of course. Usually the assumption is with big enough data, you end up with decent vectors, but you can observe a lot of biases anyway. So in my example, I observed bias towards American styles of beer, just because the data set was coming from an American website. In the Google News example, you observe something a bit more disturbing, because say the word for Mexicans, how is the word Mexican used in American news? Usually it's about illegal immigration, right? So the vector is suspiciously close to illegal immigrants, which is a strong bias. And then you observe it also with this analogy when you do king minus man plus woman is queen. If you do programmer minus man plus woman, you expect to go back to programmer, female programmer if you want. You don't. You end up with what society thinks should be a job for women. So you have all these little kind of sexist and racist remarks because they're coming from the language itself. So language is biased, and the model will pick up this bias.
Thank you for the talk. You mentioned on your last slide a comparative model to Word2Vec glove, which I think in the theory is kind of similar but a bit different. Could you comment on the differences and pros and cons of each model, if there are? Yes.
So glove versus Word2Vec, I still have to understand it. I still have to understand how they are different. They're kind of similar, and for me they're very similar. Maybe I'm missing something as well, but a lot of people are asking the same question. So the short answer is I don't know, to be completely honest. And I haven't seen, apart from the guys from Stanford, who are the authors of this model, I haven't seen any major improvement against Word2Vec. So I don't know. So it's there. I would like to understand it, so it's kind of a follow-up work, but I still don't know.
Then one quick follow-up question back to the 300 dimensions.
Yes.
Is that decision for 300 more driven by the size of your data set or more driven by the computational time it takes for a larger number of dimensions, or the text content itself?
It's just a rule of thumb. It's just empirical. That's a suggestion that was coming from the authors of the original Word2Vec paper, and they didn't provide any particular explanation. They said that we tried many options, and the the numbers I mentioned kind of make sense. So you start from there, and if you like the model, you stay there, basically. It's kind of small enough to be the fastest possible option, and at the same time big enough to pick up what you want from the language. So purely empirical.
I mean, essentially it goes boiled down to how sensitive you want to have like your data set in, right? So if you have like only one dimensions, you basically have like only one scale, like from, I don't know, cold to hot, right? And if you have like really complicated text, maybe you want to add like way more, you know, way basically to compare like different dimensionality of different ways, like those words, right? Because eventually put it like in space and you want to compare all this like a matrix multiplication that he was showing, right? It's basically the same. So if you want to like embed more of those, but you can do that. But I think it's like there's also too much of those in the end of the day. So next one.
Some people try to force a meaning on these dimensions, so that there's a notion. When I show the initial example, Rome, France, and so on, there's a dimension for being a city, a dimension for being a country. It's not true. So these are just dimensions. They don't mean anything in particular. The example was just made up to the vectors, and find these analogies between.
Presumably you could look at the vectors that you've got to get a sense of the PCA is effectively doing that. Be able to look at your PCA profile on all 300 dimensions. That would give you an idea about how many you actually need. Right? To be able to look at like the distribution of the values and effectively look at the variance of those dimensions. So post facto, you'd be able to look back and see how many that actually needed. That's what it's telling you. I don't know.
Yeah. I guess you can look at it in this way. In the case of beers, it was obvious to have this color dimension, but is it color or is it kind of toasted malts that are influencing the taste, and of course they influence the color as well? Where is the cause effect? It was a side project for me, so just for fun. But definitely you can after you train, you can have a look.
So if you're planning to feed your vector to a deep neural network anyway, how important is still like the pre-processing? I would assume like if your data set is big enough, the vector or the deep network would already like draw some conclusions that Paris is close to Rome in some way, and so is that still important? I guess like with the position of the word in the sentence, you need to code that in, but otherwise wouldn't the deep network take that job?
I guess the short answer is it depends. The pre-processing is important to end up with high quality vectors for words, so to perform this analogy task. And then if you feed these vectors into something else later and you have enough data, maybe it doesn't really matter. Or if you skip the vector training and you feed directly the text into whatever kind of model you have in mind, maybe it doesn't matter. But what I observed is you have options essentially for pre-processing. So it matters in the sense that you have options. You can choose to do a bit of stop or removal, stemming, the usual suspects. You can choose to have ungrammatical sentences and pass only the nouns, for example. With the CV and skills example, we didn't have fluent English. We had a list of skills. So literally it was based on co-occurrences, no grammar picked up whatsoever. So it matters from this point of view. Then whether it will kind of improve the overall quality, that's to be tested on your data, I would say.
Mm-hmm. Well, is there a specific procedure you would suggest for a chatbot? I don't know.
I don't know. I haven't developed chatbots.
Yeah.
I don't know.
All right.
Yes.
Hi, thanks for the talk.
Hi.
Do the vectors come out of the word-to-vec algorithm normalized, so do they have the same length, or do they have different lengths?
Are the vectors, sorry?
Normalized, or are they different lengths, the vectors?
No, the number of dimensions is fixed.
No, but the length of the vector, like the norm.
Oh, yes. So all the dimensions are essentially between 0 and 1.
But do they have the same length? So if you have two words, do they have the same length, the vector, or is it?
So what people do usually, so if you want to model a phrase, you kind of create a special token of word1 underscore word2. Is that what you're asking?
No, I guess, I mean, if you look at the mathematical object
Yes.
of a vector, it has a direction and a length. And are these vectors all the same length and just different directions, or are they different lengths and different directions?
Okay.
Because I noticed that when people try to compute the similarity between words, they first normalize the vectors and then do it. So I guess they are not normalized before.
I'm not sure I understand
Okay.
the question, so maybe we chat later.
Yeah, okay.
That's a question. Maybe last one. No? Okay. Perfect.
This one at the back. Yeah, and
I cannot see you. You're like behind the wall. I'm bringing that.
I have 3 questions for you. How big was the memory footprint in your RAM? So while you were computing with that matrix?
the memory footprint.
Yep.
I wasn't checking the memory footprint. It was fitting in memory on my laptop. The data set was the bigger one was about 1 gigabyte, so nothing huge. The output is about 150 megabytes, from 1 gigabyte of text to 150 megabytes of pickle data.
Okay. So when you're saying the output, so were you able to save that output for some later computations also? I'm assuming.
Can't hear you.
I'm asking you, so when you computed that matrix,
Yes.
were you able to save it offline? For example, you don't have to compute next time when you were, let's say,
Okay.
planning to play with the data.
So first thing, there is no matrix computed. There are just vectors.
Okay.
And you can persist the model and then continue the training later.
Okay.
So you can add more data later on, and it will, in theory, improve your vector representation.
Thank you. Yeah, it answered my third question. Yeah. Can I retrain? Yes, I can retrain.
Awesome. The last one, no? Okay, here is a winner. And after we have a break.
So I'm interested in this word to sentence stuff. Sentence to vector, genau. Yes. Do you have to predefine like the number of words in a sentence you want to match, like with a clear example, a wheat, stout, are actually 2 words, or is it just?
Okay, so the notion of sentence, as described in these papers, is just a piece of text. So it could be an actual sentence in English, or it could be a paragraph, whatever you want. And you can choose a size for a window, so 5 words before and after the focus words, or you can say, let's use the whole sentence. And usually I use the whole sentence unless I have a very, very huge data
But
set.
how's the sentence defined? Is it like with a dot, like from one dot to the next dot, or how do you define the sentence?
It's up to you in how you pre-process. For
Okay.
the CV example, the sentence was an experience in your CV, so it was not an actual sentence. In the review, I was just using, if I remember well, the NLTK tokenizer out of the box to split sentences. It's up to you how you define it, but you need to feed the sentences, so a generator of sentences to define it on your own. And how you do it is up to you. You can pass the whole document if you want.
Okay, thank you.
Okay, thank you again for awesome talk and awesome Q&A session.
Thank you.